Welcome back to Advanced Algorithms. Last time we started with the next large topic of the course, randomized algorithms. And I introduced a few elementary definitions about randomized computations and randomized computers, where we again use Turing machines as the basic model. But as you also pointed out, the simple definitions have a few flaws if you allow certain infinite computations, and some of them we would really like to keep because they make a lot of sense for many randomized algorithms. Whereas for deterministic algorithms, it was simple. If it went into an infinite loop, then it didn't solve the problem. So we were fine by just declaring all algorithms that we're interested in terminate. But with randomization, it's not so easy. With non-determinism, we also had the same problem in principle. But since we only needed one accepting run, things were also simpler. And also, we didn't have to assign a probability measure. So to fix these definitions for the general case, I found that it's not avoidable to dig a bit deeper into probability theory. Not too much, but a bit, and I'll abuse this kind of digression to also rehearse the basic concepts of stochastics that we will encounter later in the course when we analyze randomized algorithms. So the basic model was that we have deterministic Turing machines, but additionally they have an input tape that's filled with an infinite sequence of zeros and ones. And we assume that these are chosen so that each position is identically chosen of all others, and with the same probability 0 and 1. But here already the interesting part starts, because this is an infinite sequence. So it's an infinite word over the alphabet 0, 1. And we draw essentially a uniform word over this set of all infinite words. And this is not discrete. This is a continuous model. Oh, well, it's a dense model, so it's a continuum. The set we draw from is a continuum, because it's essentially, you can represent these infinite strings as binary representations of numbers in the interval 0, 1, for example. Right? So it's essentially the real numbers. And they are, of course, not discrete. They're uncountably infinite. And that's a bit why I simply said here we have this probability space. And in the end, it will turn out quite fine to just write it like this, that there's some well-defined measure of probability for these sequences. But a few details are maybe less obvious. And they were even a bit less obvious to me than I thought at first. So admittedly, this was a bit oversimplifying. This also has consequences to the following definitions here, counting the number of random bits that we need, assigning probabilities, and also determining expected and worst case time. So let's insert here a little digression on let's first look at a simple example that makes clear what I mean by infinite computations that we would like to keep. So here's a simple example of a randomized algorithm. This is even an algorithm that is supposed to have a random output. We would like to simulate a fair die. So with the 6 outcomes 1 to 6, in our model of Turing machines with only random bits. And you can think about it for a moment. It's not possible to do that, guaranteeing a constant number of bits easily. But there's a simple rejection sampling method. You first draw essentially a number uniformly between 0 and 7. This is possible because the cardinality is a power of 2. So you can just draw bits and interpret them as the binary representation of the number. But then there's two numbers we would actually not like to have, namely the 0 and the 7. And if we encounter those, we just repeat the procedure. So it's clear that this So it's clear that this procedure might run for forever, basically. But whenever it finishes, it certainly outputs one of these 6 outcomes with equal probability, because they were one of the 8 outcomes that we chose with equal probability, and we conditioned on the case that we don't have the 2 we don't like. So it's certainly a correct algorithm, but we might have a problem, or maybe not, with the fact that it can run for infinite time if we are just continuously unlucky. On the other hand, the expected running time is easy to compute. In each iteration, we have 6 outcomes that make us terminate out of 8. And if we compute the expected time, then this is just the number we sum over all numbers of iterations of the loop that are possible. And let's, for the moment, ignore the question whether there's non-zero probability of really looping forever. You can easily convince yourself that this possibility is not there, so it has probability 0. Even though it's not impossible, it has probability 0. So for expectations, it's basically non-existent. So we sum over all finite numbers of iterations. That's the probability that we didn't stop before, and that's the probability that we stop exactly now. And if you sum up this, it turns out to be a very small number. So in expectation, you don't even need 2 iterations. Usually 1, sometimes 2, and if you're a bit unlucky, then a few more. So it's a correct algorithm, and it's also practically efficient. So we certainly would not like to exclude these algorithms from our discussion. But this is actually already one that's not completely trivial. And to show you why, let's suppose we draw a large trie, an infinite trie of the random bit sequences that the algorithm uses. So we start at a root, and then we have 2 branches, namely whether the first bit is 0 or 1. Then we do that one more time, and a third time. That is just to simulate the 3 choices that we make in the algorithm for a single iteration of the loop, right? 0, 1, 0, 1, 0, 1, and so on. Now, after one iteration of the loop, the bit pattern all 0 or all 1 are the bad ones. All others terminate. So we can replace these, say, by some leaf in our representation. So we have 6 leaves where we terminate, but the other 2 now essentially recursively look the same. So we start again with drawing 2. And then one more, and a third level. Now, once again, okay, these are actually leaves. I hope you're fine if I skip the labels now. Let me just, for symmetry, draw this also. Maybe we can also leave out the leaves. But then here, the whole thing continues. And this goes on for infinity. So every 3 levels, we essentially double the number of possible computations that still run. Okay? So this is certainly a huge number of possible computations for this algorithm. It would all be simple and fine if there was some upper bound, so some depth in the tree, so that there's no active node. There's no node that is not yet, okay, no path that goes deeper. then everything is finite. Then we have only finitely many choices for the random bits sequence, and then we can for sure use some basic discrete probability stuff. We might also be fine if there's just one long branch that continues going, and then we have a possibility to stop by a single bit. That's the simpler case. Then we never have this large number of active nodes. We just have one long path. And then the overall number is still countable, right? Because it's essentially just a finite number of things per depth. Or a bounded number, sorry. Finite it's always, but it's bounded. Whereas here it's not. And this is something. So what's the number of sequences? So random bit sequences that correspond to an infinite run. Maybe not so clear, but we can look at the set of these. Now, if we represent some infinite sequence, so let's say omega is an infinite word. So this is maybe a good point to also introduce this notation. We can write the set 0, 1 to the n to mean essentially a function from n to 0, 1. Because these infinite words are just indexed by the, it's just a function where we can access the ith bit. And such an infinite word corresponds to a real number by just writing 0 dot and then omega. This is not perfectly isomorphic because certain numbers have several representations. Because you can have a sequence that only has ones, which is then the same as if you replace all these ones by zeros and add one of the position before, right? So the number 1, 1, 1, 1, 1, 1, and so on. Okay, this is actually a bad example. This one. This is actually the same as this. There's no, the numbers are the same, but the sequences are not the same. So this is not exactly isomorphic to the real line, to the interval 0, 1. But this is a real number in 0, 1. And it's at least a surjective mapping. But it's not injective because certain sequences map to the same number. Is that clear? This is actually the same problem you have with all decimal representation. It's not a feature of binary. You have the same problem there. You usually forbid an infinite trailing sequence of 9s in decimal representations. Okay, but this doesn't cause a lot of problems. Now, if we go back to our tree, what kind of sequences do have this infinite run behavior? Well, essentially just those that consist of blocks of identical digits, because these are always going on the outside of such a small part of the tree. And you can alternate between them as you wish. And this set is of course essentially of the same cardinality as this in an isomorphic sense, so you can biject the two. But in In a measure theoretic sense, it's it's still uncountably infinite, but it's small inside of this in a certain sense. So for those that have already seen a bit of measure theory, this is a set of measure 0, actually. Now this is related to the Cantor set. I just wanted to mention that, which is, so the original Cantor set is given by the following recursive construction. You start with the interval 0, 1, and then you always cut it into 3 pieces, and you delete the middle one. Now you recursively do that here. Okay, I will soon get problems with the resolution. Okay, yeah, I think I cannot even properly draw the third iteration. You can imagine that this gets less and less line filling in a sense, but still the resulting set is uncountably infinite. It's of a very similar shape. In this case, you have, so the original Cantor set, if you cut out the middle third, then you're looking at ternary representations of the numbers, and you exclude all numbers that ever have a 1 in their ternary representation. This is very similar to this. It's just a different ratio of exclusion and inclusion, but that doesn't change a whole lot. Well, there's a certain theory behind these sets, but this is not so interesting here. But the good news is that these are actually not problematic sets in the sense of probability theory. We can deal with those. So it's a measurable set, and actually has measure 0, which is intuitively clear maybe if you just look at the picture, but you should be very careful with that, because another famous set of measure 0 is the set of all rationals, which if you try to draw it, all the rationals in the real interval 0, 1, that looks pretty dense. But we know that rationals are countable, so they must be a measure 0 set. In fact, so Q restricted to 0, 1 is a much, much smaller set than this Cantor set, even though it doesn't really look like it. Okay, that was a bit of a digression. That just should motivate that, A, we have algorithms that look very reasonable and are reasonably useful in practice, but still they yield mathematical structures that are not well handled by discrete probability. So let me say it again. This is a uncountably infinite and continuous set in a certain sense, at least. So we cannot use discrete probability here. Another interesting question here is, how will we define the length of the random length of a computation? So at least for this algorithm, we know that there are computations that are infinite. It's not just for every number we find a longer computation. There are infinite computations for certain infinite sequences of bits. And we should have a sound definition of what the length of a computation is in this scenario. And that's where the trouble starts. So with this, let's go back to what I wanted to mention here, just to summarize that again. What can go wrong in a randomized algorithm? So you've already seen this tree, the trie of all these infinite sequences that gets truncated when a computation terminates. So what's possible in such a trie? Maybe let's, if you like, you can add the deterministic steps in the tree so that this actually doesn't, this step doesn't ask for a random bit, but just does some deterministic computation. And then it's not a trie anymore, but just a way to visualize the computations of a randomized algorithms. And this here is, you ask for a random bit. Then you can have the stupid case that this is an infinite loop, but one that doesn't ask for random bits anymore. In principle, this is possible, but we certainly exclude these because they're not helpful. So without further branching, we don't want these. But this is the same as in the deterministic world. The more interesting part is we could have what we've just seen before. There might be a terminating computation sometimes. And you could have such an infinite run. If it goes on like this, then you just have one long infinite computation, and you can stop at any time, but there's no branching. That's one thing. But we can also have, like in the example I've just shown you, cases where you have an infinite number of infinite computations. Okay, deterministic and infinite. And these are both the cases where there's really one run that is infinite. A different setting, at least in theory, is that for every n, there is a computation that's longer than n. This is not necessarily the same as the existence of one infinite run. But in terms of such a tree, we should have a path to go there. So these two cases will be hard to distinguish. And all these three cases are problematic for the definition with the maximum that we stated last time. Right, so let's first fix the last definition. We already started with that here, but as it's best to write explicitly the different cases that can make this go wrong. The running time, so this is again, this is in a sense a worst case running time for a single input, right? It's worst case over the random choices, which is a strange thing, but it was our compromise because the expected time will sometimes be hard to determine and can also be misleading in a sense. We'll talk about that maybe later. So the worst case time on a certain input x is infinite if there's an infinite computation. That's the easiest part, and we would not like to have that. We could also have that for every n, there is a computation that's longer than this. And we can also define a finite worst case time. And only in the cases where these two things don't happen, we define it as the longest computation. Now for this here, we just include max as one of the numbers that we can compute with. Yeah?
Are the first two infinites not basically the same? Because whenever you can always find a bigger computation, can we not always find an infinite computation?
You can always construct it in a sense. Yeah.
I think the second case isn't possible without the first case because we have finite branching. And by Königslemma.
Right. Yeah. You're right.
So are they the same?
Is arbitrary length the same as infinite length?
What? With finite branching, arbitrary length is essentially the same as infinite length. Yeah.
I mean, we could have that any given computation terminates, but there's always a longer one.
But then you have to get to it. So if you have for every length computation of this length, then you also have to get to this computation. And you know there's even a longer one. So you have to be able to elongate this one. You can go on like this.
Infinitely many of them have to lie on the same path.
Yeah, okay.
So for the expected time, this is also just the good case. Let's make room for that a bit. Here we actually have one more case. The expected time is infinite if there is any single infinite run, because then we would include that so with positive probability. Well, this is actually again we have the two that collapse. So if we reach an infinite computations, could be many with a certain positive probability, then the expectation is infinite.
Is there an example of an algorithm that has an expected time infinity with that is not the trivial algorithm that just does not terminate ever?
You're asking for an algorithm that has infinite expected time, but it's not just running into an sort of boring loop.
Yeah. I can't even think of an example for the first case. So it's questionable.
So the point is that, I mean, if this case happens, then we certainly have what you're asking for. And the point is that this here need not exist. There's just random variables where you can't properly define an expectation. Or it can be infinite. So this in general will be an infinite sum. And it need not, so it might just be divergent. And you can cook up examples where this is not completely obvious. So where you certainly have a certain chance to terminate. So it's not that you're locked up in an infinite loop, but these chances to terminate just don't come often enough. Does that make sense? So say you terminate with a constant probability, but only after an exponential number of steps. Whenever you didn't terminate, you wait twice the time till you try next. Does that already suffice? So you should set up the sum. I mean, it's a sum like 2 to the I times some other geometric series. That's maybe a good example for the exercises. We have a last definition of this kind, and that was the number of random bits. So and this is again just infinite if there's an infinite computation. The point is that it should be a computation that also consumes random bits. It's not enough that it doesn't terminate, it should also consume random bits. Otherwise, random could still be finite when time is not. But this is not an interesting case. Okay, so far so good, but we still have to talk about the probability of a computation. So here this simply says this is the probability of the sequence of random bits that led to this computation, which is fine if all our computations are terminating, so that we only ever have finite sequences of bits. But we will come back to this in a second. And then also this expected time also implicitly depends on this. So let's talk about probability theory. This is a lot of definitions, but most of them should be reasonably familiar to you, and we will mostly not have to deal with the most general cases. But for this first chapter, where we try to deal with the largest possible family of randomized algorithms, we can't avoid dealing with the general probability spaces. So let's briefly discuss that. What you usually should have seen is the discrete case. There's a finite or countably infinite set. That could be just the natural numbers or whatever you like that you can map into them. That's the set of our elementary events. And a probability measure on such a probability space has to fulfill these properties. So it's a function that maps subsets of this probability space to 0, 1. So it assigns a probability to events. We will, on the next slide, say that an event is essentially a subset of these events in omega. So to make a specific example, if you have just a die, then this would be the numbers 1 to 6. And an event could be that the number is even. So let's just write it like this. Okay, then this is just a set of numbers. And in general, this could also be infinite. And then the events can also be infinite. But in the discrete case, they must be countable. For for this to count as a probability measure, it has to assign 1 to the whole set, and it has to be additive on the disjoint sets, which in this discrete case can simply be written if a set is consisting of these small omegas, then you can sum up their weight to get the weight of the whole set. So what you will also use is the probability weights fix the probability measure in the discrete case. You only have to design for the weight, for a weight, for all of the numbers in your discrete space omega. Okay, so in this case, a fair die should say the probability of each of these is 1/6. But you could have different weights. And another example, maybe you could have the naturals as your set, and the probability for I could just be what we had before, 1/4 to the I minus 1 times 3/4. That would give you the number of iterations of the roll die procedure, which is also called the geometric distribution. And we'll see that. And in this case, any events are just some subsets of the natural numbers. So this is the easy case. Now if we want to deal with probability distributions over different sets that are more infinite than countable infinite, we have the problem that we can't define the probability of a set by simply assigning weights to all its elementary events, because there's no way to assign them a non-zero weight without violating this. So in general case, if omega is continuous, then all these elementary point sets must have measure 0. And then things get a bit more involved, because actually from a continuous set, there's no consistent way to assign all subsets a sensible measure. We've seen the Cantor set, which already was a bit unintuitive what the measure should be, but this is one of the harmless sets. We can assign a measure for these. But there's also there's also sets where you can't assign a sensible measure, so you have to restrict the set of allowable events from all subsets, from the power set, to some restricted set, which is this F. And formally it's called a sigma algebra, which just means that it has sensible closure properties. So it should contain the empty set, and it should be closed under complementation, which immediately means also that omega is in F, which we actually need down here. And the second interesting thing is, if you have a countably infinite, so a sequence of events, then also their union is in F. And this is actually an infinite union, but it's countably infinite. So you can assign these sets an index. It might seem that this doesn't make a big difference, but it does, because it's the difference between being able to sum over all the elements in a sensible way and being not able to do that. Because you have complement and you have union, you can also do countable intersections and so on. So usually this F is a rich enough set so that all sensible subsets can be expressed in that. So let's give an example of how this looks like, because this is a bit abstract, I agree. A typical set for omega might be the real interval between 0 and 1. And then the question is, what could F be? And the usual choice for F is the sigma algebra of Borel sets. And this is essentially the closure of open intervals. So you say for any A and B, that's a subset of this should be an F. And then you close this set by applying all these rules. So the complement of such a thing is in F, and the infinite but countable unions of all these sets are also in. And that's how you can show that the Cantor set is essentially in, because you can represent it as a countably infinite intersection by just following the recursive definition. And that's why it's not so bad after all. So, and then you close it, closure. That this really works and exists is nothing that we will talk about. We will just silently assume, if we talk about the reals, that there's a suitable sigma algebra. And the point is that this is rich enough, so it's hard even to give an example of a set that doesn't have this shape. So you can look it up on Wikipedia if you like. Yeah, there's a construction given which is esoteric enough to show the flavor that these sets must have. Okay. In the general case, also the probability measure is a bit more difficult because, as I said, we can't just sum over the elementary events. But it follows similar rules. It must assign 1 to the whole set. And whenever we have disjoint elements, disjoint events, so disjoint elements of F, which are subsets of omega, then the measure must be additive, which is an intuitive requirement if you think about length as the measure of these sets. So there's also a natural choice, which is Lebesgue measure on the reals. That's just the formal generalization of length of intervals. So this measure on such an interval AB would just be, as you expect, the length of this interval. And via this rule, you can assign such a value also to such unions of sets and complement via 1 minus and so on. So I don't want to go into too much detail. The point is just that for the simple sets, it's the length of the intervals. And as long as it's just a finite union of those, it's all trivial. And for everything else, there's a way to make this work for the whole Borel sigma algebra. And we'll just take that for granted. I mentioned this because we will need another one for our trees. For our trees, okay, maybe I should say that again. If you restrict our attention to algorithms that have a well-defined worst-case time for every input, so there's an upper bound on the runtime for every fixed input. That means that there's only finitely many different computations for a fixed input. Then we don't need all this stuff. Then for any fixed input, we can define a discrete probability distribution, which is actually just a finite one, which makes it even a bit simpler. But to cover the general case, we need the following construction. So our ground set is the set of all infinite sequences. Now we need something that corresponds to these intervals. And these are the prefix sets, if you like. So they're also called cylinder sets for x a finite word. Any length but finite. Then this is the set of all infinite sequences that start with x. So you might think for a second how you would formally define concatenation for these if they are represented as functions. Not so hard to do. So these sets are essentially fine. They also, in a sense, naturally correspond to an interval, because if you take these infinite sequences as representations of real numbers by binary representations, starting with 0 point and then the sequence, then this is just a prefix of that sequence. So it's a certain interval. So it's an interval of the shape, okay. Oops. Oh, come on. 2 to the minus length of the word. And also a must be a so-called dyadic number, right? Which is nothing more than saying that a times 2 to the n is an integer for some n. So it's a rational number where the denominator is a power of 2. These are just the numbers that have terminating binary representations. So it's not so surprising that we have something like this, but still it's coming up with this representation is a bit of a step. Now we take these as our ground sets and we again apply the closure. So we use these rules to complete our set F, and then that gives us our sigma algebra. Okay? Now we also need a probability. And okay, this is something I also didn't mention. The probability is essentially fixed if you fix it for all these ground sets of the sigma algebra, because all other sets are formed using these rules from the ground set, and the axioms of probability measures essentially just tell you that you can compute along these constructions what the measure of the composite set is. So in principle, we just have to define what the probability of these cylinder sets is. And we just define that as the probability for x if you are just ignoring that there's an infinite part behind. But this makes again sense if you look at it's exactly the length of this interval, so that makes a lot of sense. Oh, this should be an x, I'm sorry. Okay, so we would probably like to check that there's a way to represent interesting events. So can we, for example, for a single non-terminating computation, we will have one single infinite sequence of bits. Can we assign that a probability? We should be able to do that. And if it was anything else than 0, we should be concerned with our model. But formally, we have to show this in our setting. And by that, we should first show that the singleton set that actually has to go into this. So probability talks about sets of subsets of omega. So this singleton set, is this at all in F? That's the first question. And yes, it is, because we can write this as the countable infinite intersection. Okay, let's just sum over I, and then the pi set, where we take the first I letters of this infinite string, and we fix that prefix. So note that with pi, there's no way to express an infinite prefix, but with a countable infinite intersection, we can still express it. Yes?
Could we not just say that is pi with x equal to the empty string?
That's not the same. So for I equals 0, this would be pi epsilon. Maybe that's a good thing to note. Pi epsilon is actually all of omega, because it says it's all infinite strings that have the empty string as prefix, which is all strings. Right? So and along this composition, we can compute the probability. Okay, using a rule that we will see in a second. So because this is the intersection, it doesn't directly work with our with the defining rules, because this is only for disjoint unions. But we can essentially so in a second we will use the following, show the following rule. If we have to compute the probability of an intersection, we can take the probability for the set A alone and multiply by the probability for A given B. So this is the conditional probability. And if we iterate that construction, we can compute this. So this is just rewriting. And then we can take out the first of these sets is pi epsilon. And then iterating that rule gives a long product where in each case we have the next set, 1i, conditional on all the previous sets, 1, 1, up to I minus 1. So this is fine because for every I it's a finite thing. And intuitively the intersection of these is just the last one. So this rule works in general, but since our sets are nested, each is a subset of the former, this actually collapses. So and then we're asking here for the probability that our infinite string has a certain prefix of length I, given that it has the same prefix except for the last symbol. So that probability is just 1/2 because there's only one additional bit that we're interested in. So this whole thing is 1/2. And now we're taking an infinite product over 1/2, so this is exactly 0. That was a long and tedious proof for something that we already knew must be true. I just wanted to show that the theory is in a sense sound and that you can work in that setting, even though it's an inconvenient setting in general. But it works out if you ever have to go down back to that detail because you're dealing with a non-terminating thing. you can do that. Yes, questions?
In the formula about should be B given A.
Yeah, sounds reasonable. It should be on one of the slides. Let's check whether it's correct there. Okay. I spent a lot of time on this. Let's do a bit fast forward. I've already talked about events. These are the elements of F, which are subsets of omega. There's a few simple properties. This is almost trivial. The counter probability is 1 minus the probability. A useful thing is called union bound, or also known under different names. The rules for probability measures was if we have a disjoint union of events, then the probability of the union is the sum of the of the probabilities of the single sets. And in general, you can at least upper bound it by that. Now this is the important notion of independence. A set of events is called mutually independent if the probability of the intersection factors into the probabilities, and this must be probability for AI, of course. I stress mutually here because you can also define k-wise or just pairwise independence if this is only true for subsets of a certain size. We will maybe talk about that with respect to tail bounds a bit. Conditional probability is something we already used. Here's the formal definition in terms of elementary probabilities. If the probability for this event B that you condition on is 0, then all kind of inconsistencies can happen. So this is just formally not well defined. Here you divide by 0, which should be a sign that there's something going on. There's a formula, the law of total probability, that is not exactly what we used before, but similar and in disguise. If you have a partition of the whole set, then you can compute the probability conditional on all of these individually and average over them. I guess you might have seen that before. Maybe you don't recognize. So that was about events. A more important notion for us is that of a random variable. The measurable space that or the probability space that we work in should typically be thought of something abstract where you can't compute. And if you want to compute, then you use a function to map this omega to some set where you can compute reasonably. And often this is the real numbers, but it might also be vectors or matrices, or if you're creative, something else. And a random variable is just any such function, where in general spaces we have to ensure that this function doesn't destroy measurability, which is again something where you have to work hard to get it wrong. Okay, some basic conventions. Notations for writing the event that a certain random variable has exactly one specific value. You can write indicator variables for an event. So that's, if you're given an event, you can define a random variable that is 1 exactly if that event happens and 0 otherwise. And then for random variables, you can also talk about their distribution, which is in the general sense, the distribution is given by the cumulative distribution function, so this function. where x is the parameter, you talk about the probability of being at most x. If x is discrete, then no, the other way is, sorry. The discreteness of a random variable is not necessarily the same as the discreteness of the probability space it's defined on, but it depends on this x that the random variable lives in, so the value space. And if the image of all events is a countable set, then x is a discrete random variable. So you can certainly start with a continuous or with a general probability space, something on the real line. Say you start with a uniform point on the real line, but then your random variable is something like an indicator. Is it greater or equal than 1/2? Then this random variable is discrete again. If we have a discrete random variable, we define the probability mass function like this, because then we can talk about a sensible probability for isolated points. If it's not discrete, then in general, it's tough to grasp this random variable. But there's the case where the distribution function can be derivated. And this derivative is then called the density. This is again something that in general it does not always exist, but we will hardly deal with cases where it doesn't exist. So, and if it exists, then the density is a helpful function that characterizes the distribution. As for events, we can have independent random variables, which formally means that they're joint. Let's cross out these. That they're joint probability density or mass function factors. So you can, with a general definition where x can be just any set, you can also group a few random variables as a vector, and then this is a vector-valued random variable, where you have x is this. And then you can talk about this guy's mass function or density function. And these are independent if they factor. Okay, so this was just a definition. I was jumping ahead. So the random variables are independent if they're joint distribution factors in this sense. Probability that they together have the values x and y is the same as if you just ignore the value of the other one. Before you doze away completely, let's consider a random variable from our setting. Namely, the random runtime of a randomized algorithm. And this is the last time, I think, where we will need the general probability space thingies. So maybe we can finish that off today, and then you can close that chapter. Let's call this the random running time, capital T. So what is it formally? A random variable is a function from the probability space to some values set. So running times, we count steps, so that should be an integer valued thing. But it takes an infinite bit string and maps that well to n or infinity. So let's include infinity here. I think I don't allow 0. So if you like, every computation takes one step before it terminates. That's just the definition of what a step is. So for sure, t is a discrete random variable because its value set is discrete, no matter how you map it into that. The question is whether it's a well-defined random variable in the first place. And since we're starting in a general space, we actually have to worry about this. Is that function that we would like to assign to t, is that a measurable function? So well, to answer that question, I should at least informally define what t actually does. And I imagine it again in our branching try. And then any specific infinite bit sequence gives you some path in this try, right? Let's maybe add a few more. And the red guy just says follow this path. Then there's the possibility that you hit a terminating node. And in that case, you just count this number of steps. If you can go on forever without ever hitting such a thing, then you say it's infinite. Does that make sense? So this is the function that I have in mind for t. Let's briefly check if this is measurable. So measurable in that, so a function is measurable if you take a measurable function in the output space, which since n is discrete is just any subset of the natural numbers. And then you take the pre-image of that subset in the image and go back to the original space. And you have to show that this is again a measurable function. So if this is a subset of n infinity, then t inverse. So this is just a pre-image. We don't talk about inverse functions, but so this is the set of all omega, so that t of omega is in M. This must be measurable in terms of the original space, so in our infinite bit strings space. And by the same arguments as before, we can restrict our attention to m's of a simpler form. Maybe open intervals. So I think half open and going to infinity. That allows you to construct all subsets by some countably infinite union or intersection. So you can build all singleton sets, and then from then on you can build all the rest. So if we look only at these sets, then we can actually show that this is measurable. And I promise then we'll leave this wicked world of general probability. So this pre-image is the set of all random infinite bit strings, so that the time of computation on such a sequence is at least k, for k some number. And we just have to represent that. So we have to show that this is an element of our F, so that it can be constructed from these cylinder sets, right? And we can easily do that. kind of. If you look in the tree, then these sets where they restrict the minimum length of a computation, essentially we take a cut in the tree level, and then we have to find all the pies, all the cylinders for the nodes that are still active. And we can do that by just subtracting all that are not active. And since this here, so we take all shorter prefixes, so that let's just sloppily write v of w is the node that corresponds to this string in the trie. So this is a finite union, because this is already finite and we restrict it further. And for all these terminating things, we take the pi w, and then in the end we take the complement of all of these. Okay? So we take all terminating runs and all those that terminate before k steps. The complement of those is all those that are still running. And well, this is just by this construction an element of our sigma algebra view. Okay. This doesn't guarantee that the expected time is anything sensible. It might still happen, as we discussed before, that E of t doesn't exist. But we haven't formally talked about expectations. So let's briefly finish this probability introduction, because I think the rest is simpler for you. If we have a random variable x, then E of x, the expectation, is in our case one of these two things, because we will only ever deal with either discrete variables or continuous ones with a density, and a density with respect to Lebesgue measure for the experts. And then you can write the expectation, you sum over all possible values of the random variable, you multiply the value itself by its probability and sum over all this up. You've seen that before. And in a continuous world, summation becomes integration, and the probability itself must be replaced by the density just to make things work. Okay, because any isolated point here doesn't have a non-zero probability, but with the derivative of this probability function, you can define a sensible value. And in both cases, these might not work out, so it might be that they just don't converge, or they might be infinite, whatever. You know that the expectation is linear. Let me add that this only works for finite sums. Maybe something easily overlooked. And it works also if they're not independent, but if x and y are indeed independent, then also the linearity, the expectation factors. We had conditional probability. We can also define conditional expectations, which, if x is a random variable and a is an event, I only define it for discrete x. Then we can simply use the conditional expectation instead of the normal one. And there's an x missing. So this would be like the definition for expectation, just with conditional probability. For continuous variables, this is a bit more delicate to define, but a specific special case is often helpful, and that's why I included it. We can condition on such a special event, namely that another random variable has a certain value. And we can even do that if y is continuous, even though then this event itself has zero probability. The following definition is still well defined, which is per se not trivial or not obvious, but The definition with the densities makes it work. But okay, I'm already too far. For discrete variables, we define this using the version above, just inserting for a. And in the discrete world, then we essentially exclude values y so that this has probability 0. Because then, again, this conditional probability is not well defined as before. So it's not legal to condition on probability 0 events in general, except for this very special case if it's defined like this. So if we have two continuous variables, and then they have some joint density. So I define continuous that we have a density, and we'll always have for our examples. The marginal density of y is just the density of y alone, which we can compute from the joint one if we integrate y out. That's how people sometimes call it. You can formally write it as this. So this notation means you integrate over all values in this x, which if x is the real line, then you integrate from minus infinity to plus infinity. And then often for certain values, this density will be 0, and then the range actually is smaller, and so on. But the interesting part is, what's the expectation of x given that y has a certain fixed value? This is given by this. It's like the definition, it's on the last slide, for the ordinary expected value, but we replace the density by this conditional density, which is the quotient of the joint and the marginal density. So this mimics exactly the way we defined conditional probability, but now we use the densities. And that's a way to make it work like this. Okay, all this conditional expectation stuff has exactly one nice application, and that's the law of total expectation, written in this deceptively simple form here. I should say that if we take a function here where y is a parameter, and then for every y, this is the value, we actually get a new random variable. Usually the expectation is just a number or an element of this universe for the random variable. But if we write the expectation of x given y, this is a random variable that is a function of y. And this is sometimes helpful. Let's, as a last thing, give you a very made-up example. Let's say you first, okay, one more notation that I came to like a lot. Equals with a d on top of it means equality of distribution. So this is a concise way to say p is a random variable that has the same distribution as the thing on the right. And this b of p is my abbreviation for the Bernoulli distribution with parameter p. So this is just a coin flip where p is the probability for 1, and otherwise it's 0. So 1 or 0 with probability p, and otherwise 0. That's an easy thing. And now define, I made a mistake. This is the second step. Let's call this x. Okay, we can leave, let's leave b of p like this. X should be a Bernoulli variable, but now I want to insert a random probability, okay? And that probability could be, for example, uniformly chosen from 0, 1, okay? Okay, it's a made-up example, but one that in maybe a slightly different form might come up in certain applications. You first draw a random number, and then this number is used as the parameter of a different distribution. Okay, some of you know applications for that. Maybe I'll in the talk in the last session. Maybe I'll tell you a bit more about that. Now, so sometimes you just have things like this, a random variable defined on top of another one. And now if you want to know what's the expectation of x, this is actually a tough thing to compute in general if you have stacked a few of these on top of each other. But with the law of total expectation, it's pretty easy to compute. Maybe something you can do at home. Okay, let me just check. Yeah, that's all I wanted to say about the probability theory stuff that you probably also already know about. So in that case, it's a recap. A few things might have been new because the general probability space is sometimes left out. And especially in lectures on randomized algorithms, it's often left out. But I found it comforting that we can reasonably define that also for the non-terminating runs. Because this was a lot of hassle, we will in the future try to stick to algorithms that terminate after a guaranteed worst case time. After all, we're thinking about applying algorithms, and these should not just run forever. But the sampling example from the beginning with the rejection sampler shows you that sometimes it's quite a good idea to keep these options open. We will see next time that we can mostly avoid it. Okay.